Alright, welcome to the E6-B tutorial. First thing we're going to be going over is conversions. So conversions are used quite a lot and definitely an important thing to know. So first things first, we got to find the different markings that are related to the conversions. So I'm sure you've seen it on your E6-B, all these little symbols and markings such as feet, US gallons, statute, nautical, they all have these little arrows. So those arrows are all for the conversions. So let's go ahead and line up two of these arrows, US gallons to liters. So there we go, as long as these two arrows are lined up, now this entire wheel is converted for these two things. So US gallons is going to be on the outer ring and liters is going to be on the inner ring. So what that means is 1 US gallon converts to 3.8 liters. And this works for all different arrows. The important thing to note is obviously you can't really convert gallons to meters just because that simply doesn't make sense. So got to make sure you're thinking logically here. Another kind of common one is going to be nautical to statute. So let's say we're converting nautical miles to statute miles. Pretty common conversion. So again, we line up these two arrows, nautical on the outside, statute on the inside, and let's just use 100 again. So 100 nautical miles is going to be 100 and just over 115 statute miles. And this works too for speeds as well. So knots and miles per hour, which miles per hour is for the statute. We can convert that as well. So I'll just leave this lined up. So 100 knots is equivalent to 115 or so miles per hour. Another thing I like to, or the way I do it for kind of quicker and more specific thing is, let's say I'm specifically converting one number. This happens a lot when you know how fast you're going for a cruise, let's say. So let's say we're cruising at 80 knots and I need to convert it to miles per hour. So I line up 80 with this nautical, and this little bracket leads us to statute. So now 80 knots is going to be 92 miles per hour. So I just think that's helpful because it's just a little bit quicker for specific numbers. But yeah, so that is going to be conversions. When in doubt, just line up the arrows and look at the numbers. Alright, so next thing we're going to be going over is multiplication and division. So first things first is knowing what we are going to be using in reference for multiplication and division. And that's going to be this 10 with a black square around it. So what I mean by that is we are going to line this up, or it's going to point to an answer for multiplication or division. So we'll go ahead and do multiplication first. So let's do 8 times 11. So I have my 8 number, and I line up this 10 with it. And this goes either way. I could line it up with the 8 or 11. I'm just going to choose 8. And then on this inner ring, I'm going to find what I'm multiplying it by. So in this case, 11. And that leads right to 88. And we know 8 times 11 is 88. So that's perfect. Another example is 8 times 8. That leads to 64. 8 times 20. In this case, it leads to 16. Now we know 8 times 20 is not 16, it's 160, right? So important thing to know is when you're dealing with bigger numbers, you kind of got to know how many decimal places to add for that. And let's do one more example here. So let's do 15 times 5. So once again, on the outer ring, we have 15, and we line it up with the 10. So now on the inner ring, we want to find the 5, which is what we're multiplying it by. And right there lines up to 75. And 15 times 5 is 75, so that's perfect. And it's important to note, if you like, you can do it either way. meaning if I line up this 10 on the outer ring with this 80 and go the other way and find the 11, it'll also line up to 88 and any other number. So that's just my preference to use the 10 on the inner ring, but you can use either, of course. So now for division, we're still going to be using the 10, but it's going to be a little bit different. So I like to think of it as a numerator and denominator, like a fraction. So let's do an easy example here. 10 divided by 5. So we have 10 on the outside and 5 on the inside, just like a fraction would be. And then the other 10 leads to our answer. So 10 divided by 5 is 2. Again, with the decimal, we know it's not 20, right? So let's go ahead and do another one here. Let's do 9 divided by 3. So we'd have 9 on top and 3 underneath it, and the 10 is going to point to 3. So obviously 9 divided by 3 is 3. So yeah, biggest thing to remember is just to use this 10. And that is it for multiplication and division. Next thing we're going to be doing is finding the square root of things. Might seem a little excessive to know how to do that on the E6-B, but you never know. There's definitely been questions, and it's easier to do it on here than kind of doing it in your head. So let's start with an easy one. Once again, we're going to use the 10 with a black square around it as reference for this. So yeah, put it under the number that you are finding the square root of. In this case, we're going to use the square root of 9. So we line that up, and we're going to spin that until both the 10 and the 9 line up to the exact same number. So we keep turning it, and you can see the numbers are getting closer and closer, and right about there they line up with each other. So you can see the number under the 9 is 3, and the number over the 10 is 3. And that just means that the answer is 3. So square root of 9, which we should all know is 3, so that's perfect. Let's do another one. Square root of 144. Once again, we line up 144 with the 10 and keep turning it until they start getting close. So see, they start getting close pretty quick here, so you want to make sure you're going slow so you don't pass it. So right about there, and it lines up with 12. So again, 12 here and 12 here. And so the square root of 144 is 12. And that's it for finding the square root of things. Next thing we're going over is the time, fuel, and distance problems. So these are probably the most common kind of problem you'll encounter. And it's nice because the equations are right here on the E6-B itself. So if you ever forget what to do, just read this equation. So what this equation kind of telling us is the top row is going to be the outer ring and the bottom row is the inner ring. So let's just do an easy example here. So let's say we are traveling 70 knots. So again, we have our speed here, and we line it up with the black triangle. So there we go. And the distance is going to be on the outer ring, and the time is going to be on the inner ring. So we are going 90 nautical miles, let's say. So we find 90, and we go to the inner, which is time, and that's 77 minutes. So now it's important to note that all of these numbers are going to be minutes. So if a time asks for how many hours, you can either kind of do the math in your head or look at these other set of numbers on the E6-B. So meaning 70 minutes is an hour and 10 minutes, and 80 minutes is an hour and 20 minutes. So you can kind of use this as reference. So if we have 77 minutes, we can kind of assume that it's going to be an hour and 17 minutes. Okay, so another important thing to note with these equations right here is all you need is two pieces of information. So let's say we just have miles per hour and distance, like we just had. We can find time. If we just have distance and time, we can find our speed. If we just have time and speed, we can find our distance. So let's do another example. So let's say we are traveling 100 nautical miles and it takes us 80 minutes. So again, we have our distance on the outer ring, 100, and our time on the inner ring, 80. Now the arrow is going to point to the answer, 75 knots. So now we can do another example here. Let's just have time and speed. So let's do 50 on the speed, and time, let's do 15 minutes. So we find minutes on the inner ring here, and it's going to be 12.5 miles. So that is pretty much it with that. And now moving on to the gallon equation. Another thing to note with the distance, time, and speed equation is that if you are using knots as your speed, the distance will be in nautical miles, and if you're using miles per hour, the distance will be in statute miles. So just important to be aware of that. Alright, so for the fuel equation, very similar to what we just did up above with the distance, time, and speed. So let's do an example here. So here we go. We got 5 gallons per hour. So gallons per hour is lined up with the black triangle, and total gallons is on the outer ring and time is on the inner ring. So let's go ahead and do 5 gallons per hour with 30 minutes. So 30 minutes on the inner ring here, and that is lined up with 2.5. So it looks like it's lined up with 25, but we have to just kind of think logically here, and in 30 minutes you're not going to burn 25 gallons if you have 5 gallons per hour. Alright, so got to make sure you're thinking a little bit. Alright, let's do another example here. So let's say we are flying for an hour and a half and we are burning 8 gallons, or we have burned 80 gallons. Sorry. So we've burned 80 gallons and it's been an hour and a half, or 90 minutes, right? So now it's going to point to what our gallons per hour was. So in this case, we find the black triangle, and it looks like it's about 53 and a half, kind of right in that range. And just like the other equation, all you need is 2 things. So again, if you have the total gallons you've burned and time, you can do what we just did, right? Find the gallons per hour rate you were doing. If we just have gallons per hour and time, you can see how many gallons you're going to use. And if you just have gallons per hour and how many gallons you have, you can see kind of what your range is in terms of time. And so that is it for these 2 equations here. Next thing we're going over is density altitude. So density altitude, you can kind of see a little window here that says density altitude, and that's exactly what we're going to be using for this. So density altitude, like we know, should be pressure altitude corrected for non-standard temperature. So that means we're going to need 2 things. We're going to need the temperature and we're going to need the pressure altitude. So let's just do a quick little example here. So let's say the temperature is 20 degrees Celsius at 5,000 feet. So we go ahead and line up 20, which is going to be temperature, again labeled here, right? Air temperature, Celsius. We take that notch and line it up with 5,000, and this is going to be our pressure altitudes, and they go by 1,000 each notch. So 5,000, 10,000, 15,000, and so on. So we line up those 2 things, and in this density altitude window, it points right to our answer. So in this case, it's going to be just under 7,000 feet, it looks like. Let's do another example. And this goes to some pretty high altitudes. So let's do 10,000 with -50. So pretty cold, right? We're going to be getting pretty good performance, right? So we line up the two numbers again, 10,000 with -50, and it's going to point to our answer in the window. And right here, about 4,000 feet. And that's pretty much it with finding density altitude. Just line up the temperature with the altitude, and it will tell you the answer in the window. A nice little trick to know as well, using this density altitude window, is finding standard temperature for different altitudes. So what I mean by that is if you just line up the density altitude arrow with an altitude, the temperature on that altitude down here is the standard temperature. So standard temperature at 10,000 feet is -5 degrees. And again, if we go to 0, 15 degrees Celsius, and we know that's true because standard at 0 is 15 degrees Celsius, right? So that's a nice little trick if you don't really want to calculate standard temperature for kind of higher altitudes. Just line up this arrow with it, and it will kind of calculate it for you. Next thing we're going over is converting true airspeed to calibrated airspeed and vice versa. So it's important to note that calibrated airspeed and indicated airspeed kind of go hand in hand when calculating on the E6-B. So first things first, we're going to go back to that same window we were using for density altitude. So we'll just do an example here, 10,000, and let's just do -20 degrees Celsius. So 10,000, -20 degrees Celsius, and we want to convert 100 knots true airspeed to our indicated or calibrated airspeed. An easy way to kind of remember which is which is looking right here. So on the E6-B it has our TAS, true airspeed, on the outer ring, and then on the inner ring it has CAS, calibrated airspeed. So if you ever forget which is which, just look for that. So again, true airspeed's on the outside, calibrated or indicated is on the inside. So in this case, 100 knots true airspeed is about 89 indicated. Let's do another example here, going the other way. So if we're at 20,000 feet and it's 20 degrees Fahrenheit, and we're going 100 indicated, our true airspeed is actually about 149 or 150. So there you go, as simple as that. Next thing we're going over is Mach speeds. So Mach speeds, obviously in our little 172, not very relevant, but you might get asked questions regarding Mach speeds. So if you've ever noticed it, there's something on the inner window here that says Mach number index. So what you're going to need for Mach speeds is temperature. That's going to be the biggest thing. So let's just do something random here, -20 degrees Celsius, and line it up with the Mach number. So now this entire inner ring is going to be your Mach speeds, and the outer ring is going to be true airspeed. And again, true airspeed is always the outer ring. So let's say we're going Mach 1. Mach 1 at -20 degrees is just over 620 true airspeed. If we have, let's say, +30 degrees Celsius, Mach 1 is 680, or a little over 680. So let's say we take one of those numbers, 680 true airspeed, and we want to figure out our indicated airspeed. We now need an altitude and use that same temperature. So 30 degrees, and let's say we're at 5,000 feet. So we line up 30 degrees with 5,000 feet. We find our 680 number, and about 610 is going to be our indicated airspeed. And that's going to be pretty common when dealing with Mach speeds. They're going to give you a Mach speed and tell you to convert it to indicated airspeed or something along those lines. So now if we have an indicated airspeed and we want to convert it to a Mach speed, we can do that as well. So let's say we're at 10,000 feet and it's -10 out. We're going 100 knots, or let's make it a bigger number. Let's do 400 knots indicated. So again, indicated's on the inner ring or calibrated, and true airspeed's on the outer ring. So 400 indicated is going to be 460 true airspeed. So now we take our -10 degrees, line that up with the Mach number index, and find that true airspeed again, which is 460. So it looks like Mach 0.72 is the answer for that. And that is how you find Mach speeds. Next thing we're going to be talking about is weight and balance. So there will be questions that may ask how much a CG has changed, or questions regarding how much weight was shifted given the amount of CG that was changed. So we can find both of those on the E6-B. So first, let's do the problem of someone moving from the front seat to the back seat in an aircraft that weighs 2,000 pounds. So again, they'll give you this information in the problem, and normally one piece of information will be missing, which is what we're going to find out. In this case, we are looking to find the CG change or shift. Okay, so we have a 120-pound person and the total weight of the aircraft, so 2,000 pounds. We line those two up, and now we need the station change or arm difference. So let's say the front seat is 50 and the back seat is 80 arm. And if you're looking on toll card, right, that's a number we use to find moment, right? So we have 50 and 80. So the difference is 30. So we go ahead and find 30 on the inner ring, and that leads to our CG change, which is 1.8. So if someone who's 120 pounds moved from the front seat to the back seat, the CG would shift 1.8 to the back. So now we can do another example here. Let's say it's asking how much weight was shifted, and it gives us a CG that was shifted. So let's say it moved 2.0 CG, and the difference in arm was still with that 30. So it shifted 2.0. The difference in arm was 30 again, and let's say the total weight of the aircraft was 1,400 pounds. So now we found 1,400. The weight that was shifted was 93 pounds. And that is how you do weight and balance. Alright, last thing we're going to be going over is the wind side of the E6-B. This is where you're going to find your ground speeds and your wind correction type of information you want to look for. So first thing we got to do is put in the wind. So let's just use 090 and 10 knots. So got 10 knots of wind coming from 090. And I like just lining it up on the 100 because it's a good reference for the marking. So we got 10 knots, 20 knots, 30 knots, so on, right? So after that, we go ahead and line up our true course. So let's use 130. So once we have that, we put this red dot on our true airspeed, which we learned how to calculate or convert earlier, right? So let's say we are going 130 knots true. So now this circle in the middle is going to point to our ground speed. So right here it looks like it's about 122, 123, right? Another thing it's going to tell us is our correction angle. So since it's to the left, we are going to have to correct 3 degrees. And you can see the different degrees are on here and labeled. So now if we have a more severe crosswind, right, we have a direct 90-degree crosswind and put it on 130. Now we got to turn a little bit more into the wind. But because it's direct crosswind, our ground speed is going to be the same as our true air speed. And you can also do this the other way, right? So if we want to find our true air speed and we have ground speed, we can go ahead and mark our winds once again. So let's do 220 at 25 knots. And we are going 100, or first let's put our course, getting ahead of myself here. So let's put our course at 020. So now our ground speed is 150. So now we know our true airspeed is about 126 or 127. And again, our correction angle would be 4 degrees to the left. So yeah, this is a really useful tool for flight planning, right? If you want to find your ground speed and whatnot, and those problems that ask you correction angles and ground speed. And that is it. Oh, last thing, if you ever forget kind of the process for it, you can look up at the top and it will tell you the directions for how to do it. So it has each step here and you can look at it, and then it also has kind of how to find magnetic course with the different variations and whatnot.